today. I want to welcome everyone to the Energy HPC Conference post workshop. The topic today is the emerging technologies section of those post-conference workshops. There's organizers. These are the folks that pulled the agenda together, and I want to thank them for inviting me to more or less run the show a little bit today. Just to give you a sense of where we're going. This is the last in the series of post-conference workshops that was held after the March 1st through 3rd Energy HPC Conference. And just in case you did miss it, there was some really fascinating discussions there. All the keynotes, BOF sessions and such are available at the Ken Kennedy Institute on their YouTube channel. As I said, this is the last of a series. The March 11 was Concepts of Programs HPC and AI for GPU accelerated infrastructure. On the 18th, Texas Women in HPC Workshop and the Portable Heterogeneous Programming efforts. And that brings us to today, the 22nd, and the Emerging Technology Workshop. And you'll be hearing from a number of folks today on that. And we'll get to the agenda in a moment. But just before we get started, I wanted to come up with just a quick discussion about what exactly is an emerging technology. And so I did some Googling, which of course is what you do nowadays for everything, and came up with many different opinions. So what I found was, it seems that the folks that are looking at emerging technologies most closely are folks who really aren't technology organizations. And they do lots and lots of prognostication. And what I find interesting is that every year they tend to come out with new insights, which means that as far as they're concerned, the lifetime of an emerging technology is 12 months or less. But the key to all of these estimates, as far as I'm concerned, is they really look at end uses, and they look at what emerging technologies will affecting new businesses, that they don't really dive too deep into the actual technologies that are emerging as much as some of the larger economic, commercial, or societal changes that they engender. So I thought maybe instead of looking at that, I'd look at a less analytical checklist. And to me, the two main elements of an emerging technology is their emerging technology push. What's the science-based innovation with the potential to create, transform, or in many cases, destroy an existing sector? And let's talk about from the emerging technology pull. That technology doesn't exist in a vacuum. It ultimately has to substantially alter a business or social environment. And ultimately, that technology is not yet a must-have, but maybe it's a must-have soon. And so we look at new technologies that are in a position to either replace a technology whose time has come to an end, or a new technology that will redefine the way an existing end use or create a new use evolves. The only thing that's really certain about emerging technologies is that there's a high degree of uncertainty associated with them. Return on investment, value, demonstration of end use cases is difficult, if not impossible at the early stages of development. And in many cases, it is a leap of faith for early adopters to take care of that. And what that really means is some firms prefer to wait to adopt an early technology, whether they be either a technology supplier or an end user of that. And we'll get a little bit into that in a section in my particular talk. And one of the things that I think was most compelling about emerging technologies is that the network effects matter, that the more users and more uses there are for a particular technology, the value increases in a non-linear fashion. So I really think that, to me, the theme, if there was one today from the more holistic perspective, is to think of what is the emerging technology push? What is the technology under consideration? And really, how does it create a new industry or transform an existing one? And what's the pull? What is the reason that end users are looking at technology to either solve problems they have or create new opportunities going forward that was unaddressable, intractable prior to that? So here is our agenda today, and you can see it's kind of a packed day. We're going to hear some folks we're going to hear from Argonne Labs. We're going to hear from folks from BP. Stef Simmons is going to talk to us about photonic quantum computing. We're going to hear about quantum computing preparations in the national labs, DNA compute and storage from Dave Turek at a startup called Catalog. And then I'm going to be joined by Brajesh Gupt from TACC, Jeremy First from BP, and we're going to have some closing comments. So let's jump right into my particular section. And basically what I'm going to do is kind of set the scene a little bit for how we tend to look at emerging technology here at Hyperion Research. And the bottom line here is we are ostensibly at high performance computing, or more accurately, an advanced computing organization. So we tend to look at kind of the pointy end of the spear in computing capability. So whether it be traditional mod sim on, say, an exascale system, the kind of thing that will be going into, say, Oak Ridge National Lab, or the $1.1 billion Fugaku pre-exascale system at Riken in Japan. But it also includes things like AI HPC. If you were aware that NVIDIA had their large GTC conference this week, and some of the announcements there about some very aggressive computational capabilities geared exclusively towards AI computation came out of there. We're looking at HPC in the cloud migrations. What are some of the opportunities and challenges of moving a traditional on-prem HPC workload into either a hybrid or a fully on-cloud implementation, and also quantum computing, which means that here at Hyperion Research, we tend to look at quantum as yet another tool in the toolbox to solve interesting computational problems. Whereas I think a lot of folks make this distinction between quantum computing as an emerging technology that's out there all by itself versus our impression, which is really, as I said, another tool in the toolbox to solve some of your most challenging computational problems. Let me just give you an overview of the quantum computing market landscape, if you will. This is more or less the corporate perspective of that push technology I was talking about. And this is based on a project that we completed a few months ago at the behest of the Quantum Economic Development Consortium, a US-based basically promotion group funded by the National Quantum Initiative out of the White House to really work towards the overall betterment of the domestic US quantum computing sector. And really the key to doing a market dynamic study is because, as in any emerging technology, you have a number of players who are involved or perhaps even more accurately, critical to the initiation and ongoing development of an emerging technology. So clearly the audience for trying to understand the market was, what the developers, who are the folks who are interested in market dynamics, where to go to, where the customers are, how big the market can be, and some of the more compelling questions in terms of, I'm a supplier, how can I realize some revenue going forward with this new technology? Any nascent technology nowadays is really dependent on a thorough understanding by national level policymakers who are looking at things like funding R&D, procurement policies, related policy on education, workforce development, trade, and especially for some of the more critical emerging technologies, and quantum is certainly in this group, national security consideration. Can be a double-edged sword sometimes. When you have a national security hook in your particular technology, which quantum does, certainly for some of its cryptographic capabilities, you get a certain amount of bonus funding from governments, but at the same time, it can have a chilling effect on some of the commercial dynamics if some of that technology development is considered a national security secret, or at least something that doesn't want to be shared with perhaps other countries that may be of political or military concern. Certainly, new and potential quantum computing users, or any emerging technology potential end user, wants to understand the dynamics of the market, and of course, funding sources, venture capital and such. Emerging technologies are not yet entered their virtuous cycle yet, which means they don't do R&D to generate products, to sell, to generate revenue, to fund R&D. So they're still dependent on the two major sources of funding, which is either venture or corporate capital funding, or those within the government sphere. So just to give you a quick summary of what we came out of that particular study, we ended up talking to about 112 quantum computing suppliers around the world. And we can make the analysis available because this is a data-driven forecast. It's not something that we more or less eyeballed. It was looking at some of the major suppliers around the world, contacting as many quantum computing suppliers as we could, and basically asking them some questions about their current revenues and some of their expectations for markets. So this is where we came up with this $490 million global quantum computing market for 2021, looking at an estimated compound annual growth rate for the next 3 years or so of about 22% per year, which drives us to about $900 million in 2024. Now, what's interesting is if you look at the current quantum computing supplier base out there, and this is, as I said, based on the companies we spoke to in the survey and also ones that we speak to on a regular basis, half of the companies that we spoke to had revenues in 2021 of less than $500,000 that year. And half of those, or about 25% of the companies we spoke to, had zero revenues in 2021. So there are a lot of companies out there right now, as I said, government funding, venture capital, other forms of capital funding that keep them in business to the point where they can actually start to generate that virtuous cycle. We did talk to a few companies, certainly 7% of the respondents had quantum computing revenues of over $10 million. And now that is an interesting phenomenon because some of them are what we would call a pure play company, a company that manufactures only quantum computing capability, whether it be in hardware or software. And so their entire revenue stream is based on that. And then there were also large organizations, and I'll choose, for example, say a company like IBM or Atos in France, where quantum computing is part of their overall larger IT capability. So there is an incredible blend of quantum computing suppliers out there. So it's not a one-size-fits-all solution when one tries to characterize exactly what the push perspective of this technology is. When we asked about, say, cloud, when we asked about how people would be accessing quantum computing capability, cloud loomed very large. About 2/3 of the suppliers are really fixating their distribution channels to either have an all cloud access model to reach end users or a hybrid on-prem, mix of on-prem and cloud. But the bottom line is for the next 2 or 3 years at least, the cloud access model is one that we think is going to be the primary method of end users accessing accessing cloud compute capability, which really in some sense is I think an advantage right now. The barriers to entry for a company to explore quantum computing is actually quite low when it comes to costing and resource allocation. It's not like, say, 20 years ago, where if you wanted access to an HPC, a supercomputer, a Cray class system, you had to plug down $20 to $40 million, clear a whole bunch of space in the basement, and hire a raft of technical experts to do that. So in some sense, the cloud access model, I think, is really driving the proliferation of organizations that are in the process of testing and looking at use case opportunities and such for cloud computing. And so this is really, I think, a way to go. But as organizations become more dependent on more dependent on quantum computing and start to see its business value, we're going to see a certain amount of on-prem sales ramp up, say, in the next 3 to 5 years. From the vendor's perspective, where they see the most promising sectors right now is the quantum computing market. The sector is new, and so it has to basically fund its own development. So for companies getting access to hardware companies dealing with software, it's an internally generated market in some respect, but also areas of cybersecurity, financial, academic, and chemistry were high on the list of those market segments where QC suppliers saw the greatest market opportunity. We asked a couple of questions of these 112 vendors about where they saw algorithm broken down by revenue, and I like the fact that there's a depth of opportunity here with no single one actually taking a dominant lead right now. So machine learning was the largest one, but following closely behind optimization and modeling and simulation. We saw some uptake in cybersecurity that we hadn't seen before. And I want to be clear, this isn't cybersecurity in terms of QKD or other kind of secure communications, or even the issue of the Shor's algorithm being used to break public-private encryption keys. This is more about defensive cybersecurity, using quantum computing as an opportunity for, say, real-time analysis of your overall IT infrastructure to look for anomalies that could speak to intrusions or other abnormalities in your system that could lead to a cybersecurity incident. One of the things that popped up this year, I think, that we hadn't seen much before was Monte Carlo processes. And the essence of Monte Carlo processes is the access and acquisition, if you will, a use of truly random numbers to generate the kind of modeling and simulation scenarios you need to get your work done. And so we're starting to see an uptick in people understanding that quantum-based random number generators offer some significant advantage over classical counterparts, and we expect to see that actually become much more of an interesting opportunity for some of the algorithmic use cases in quantum computing. in complementing, as I said, the emerging technology push concept, we wanted to make sure that we were looking at quantum computing from a pull concept. So we also last year did a end user study to really start to try to figure out what some of the key insights from quantum computing end users or potential end users in terms of their awareness, some of the use cases, their procurement and buying decisions, essentially their hopes, dreams, and aspirations for what quantum could bring to their world. And what we did was we made some decisions about who we wanted to talk to, and we really wanted to hit the key decision makers who were involved in the commercial sector's strategic technology planning. We didn't want to talk to quantum computing technology evangelists within the company because we thought we'd get a much more rosier perception. We wanted to talk to those in the organization that not only are in a position to make the big decisions about quantum computing uptake from a commercial perspective, but also with the ones with the authority to write the checks, the ones that actually make the hard decisions about use case advantage, return on investment, and impact on the company's overall competitiveness by bringing quantum into their workspace. We made an arbitrary decision here that we only wanted to talk to companies that had at least $50 million in revenue in 2021 and an IT budget in excess of $5 million. We just felt that we didn't want to talk to small companies that, even though they were interested in quantum computing, their abilities to implement that with any significant budget commitment was just not there. We ended up actually reaching companies that were primarily in the $500 to $1 billion annual revenue range, with IT budgets that were generally between $25 to $50 million. So we're talking about relatively large companies with a reasonable ability to address some of the budgetary concerns about bringing any new technology into a workspace. And let me just give you some of the key takeaways from that particular study. Almost 70% of the 415 companies that we surveyed worldwide, and this was not, are you a quantum person? And then we dropped down to the next questions. It was basically a random selection of leading companies from around the world. We found that 70% of them had some kind of in-house quantum computing program. And we'll get to a definition of what we mean by some kind of in-house program. We wanted to dive a little more deeply into that. But as I said, 70% that we spoke to already have it, and 20% plan to do so in the next few years. And we basically found that what that means is 10% actually, without rounding. It's about 8% of the organizations we spoke to will not be interested in quantum, at least for the next 2 to 3 years. So there's a 90% plus interest for quantum computing to come into the workspace across a number of verticals. And we'll get to that in a minute. But when we asked with the executives, what's the pull here? What's the things that they want to see out of quantum? They looked at it as being able to offer a range of corporate level benefits. And the two that were most cited were improved research capabilities and increased revenue. But the key there was that the third one was driving innovation. So of the top 3 choices that we saw emerging from this study, improved research capabilities and driving innovation were 2 of the 3. And what I really think is that shows a certain degree of long-term commitment. This is not viewed by these executives as bring in QC capability and we better see some return on investment within the next 6 months, within the next year or so. There is a certain amount of expectation that it will take time for quantum computing to work its way through the R&D cycle to result in better products, better efficiency, better business process, but not in the short term, but perhaps in the next 2, 3, or 4 years going forward. And I think that's a relatively modest expectation when you talk to these folks. They traditionally want to see some very quick turnaround and return on investment. But the understanding here is that quantum computing is a nation technology. It'll take a little time to roll out. And from a pull perspective, that is understood and already, I think, baked into some of the corporate decisions we're going to be seeing in the next few years. End users are ultimately looking for solutions in areas like optimization, factory processes, and scheduling. What it really comes down to right now, I think, from the end user perspective, is of all the applications that I think they are most interested in, the optimization angles here, the idea of taking a business process, a manufacturing process, logistics, transportation networks or such, and really turning that into how can we eke some additional optimization out of that. There are certainly other end uses that we saw, but optimization at this particular point in time was really high on the list of what end users are looking at as well. We did talk to about 17 different verticals spanning things like energy, oil and gas, aerospace, automotive, and what we found is that literally every vertical we surveyed had some significant level of quantum computing activity. So it isn't as if, and if you read the popular press, you'll see that a lot of people think that quantum computing right now is the darling of, say, the financial sector to do things like risk portfolio analysis and such. While that certainly is a high percentage of interest in quantum computing, it's not the only one by a long stretch. And we saw a really wide degree of interest across all the verticals. What was fascinating to us, and we wanted to really understand the potential for uptake of quantum computing in the companies we talked to, we asked them about the kinds of applications that they are already running, or more appropriately, the kinds of algorithms that they're already running on their classical IT. And when we asked them about things like, are you conducting data analysis, or machine learning, optimization algorithms, mod sim, research, material science research, we found that most companies are doing a significant portion of these kinds of workloads either frequently or almost always. And very few companies said they do these things rarely. So the companies that we spoke to are already in a position to understand that they have workloads that are amenable to being converted from a classical compute platform to the quantum computing platforms. And this is just some further details on those key takeaways. As I said, improving research capabilities, driving innovation were two of the top three choices. That as I said, speaks to the kind of time frames that some of these organizations are interested in. By the way, all these slides will be available if you they'll be available for me. I'll have my email at the end of this. Just drop me a line and I can not only give you these slides, but send you some of the deeper analysis and studies that came out of these particular efforts. This is where we got to the issues of activities. As I said earlier, exploring options with what's going on out there. Because we were talking to some large companies, in essence, we talked to a number of companies with annual revenues above $10 billion a year. We wanted to make sure that we gave them the opportunity to address as many efforts as they were, because we didn't want to say, okay, you have to pick either the biggest one or the most interesting one. So tell us what you're up to. And we saw that about half the companies we talked to are exploring options, monitoring technology developments. And that could be something as simple as having one or two designated people looking at quantum technology developments, scanning the popular press or such on, say, a daily, weekly, or monthly basis, all the way up to committing things like limited in-house pilot programs, fully funded research efforts. So there is some work, there is a wide range of effort going on out there, some of it relatively low resource intensive, others funding activities are already coming to the fore. Some of the chief hurdles that these companies identified, and high commitment to existing budget and IT resources. This is a perennial problem. Where are we going to find new money to do new work? So that's not a great surprise. But the one that jumped out, at least to me, was integrating quantum computing into existing IT infrastructure. And I think that's and coupling that with the second or the third one down, the lack of in-house expertise, speaks to concerns here about, well, we want to bring quantum in, but we don't have the in-house expertise. We want to drive it easily into our existing IT infrastructure. And the combination of those two factors, I think, really drive the burden of responsibility to the technology push folks. The idea that you have to be able to distribute and drive your emerging technology into an end user site without that end user having to commit too many resources to getting it, standing it up and making it work. I just want to make a quick little pitch here of sorts. One of the things that we're working on right now here at Hyperion, we've been part of an effort that's responding to a U.S. congressional request to identify and more or less quantify some of the potential supply chain issues that are going on with quantum computing. I mentioned earlier the idea of quantum computing viewed as a strategic technology, both here in the United States and quite frankly, in most other nations around the world. And so there are already some concerns here about securing supply chain stuff. So you may be hearing more about this in the future, but this to me is one of the more interesting aspects of any emerging technology nowadays. It's no longer just about the technology. It's no longer about its commercial application. There are so many more interesting elements that go into it, whether they be societal, commercial, defense related. Technologies of interest in the emerging technology field simply can't be viewed anymore as just that, a scientific development. They have to be viewed in a much larger scope of what's going on. Now, and this is what we did is we went out and we're talking to a number of organizations around the United States, asking them a whole bunch of questions about supply chain vulnerabilities. And I think we have to get something up to the hill, I think within the next 4 or 5 weeks. So keep your eyes open for that. And if you want to know more about this particular effort, we're always willing to find out what people are concerned about, opportunities to further the discussion, to make us a little smarter on some of the supply chain issues in quantum computing specifically, or in emerging technologies in general. So that's, like I said, it's a whirlwind tour. I want to stay on schedule today. That's my goal. And so if you have any questions or comments, either hold them to the end of the day here or drop me an email. And which reminds me, I do want to say that for the series of speakers that follows next, what we're asking is for folks to listen to the discussion. If there's time for questions at the end, that's great, but we'll only take a few questions if we have time. Otherwise, we'll wait to the session at the end of the day if we have time. But we will capture all the questions that are written down in the chat at the bottom of the screen there. And if you have those, by all means, put them in the chat and we'll try to address them at a later date. But in terms of questions, wait till the speaker has more or less finished before you ask questions, or submit them through the chat and we'll try to get to them at the end. But that's all I have to say today. So what I'm going to do now is turn it over to Venkat Vishwanath, who is going to give us a little bit of discussion about Argonne AI lab and evaluation of unique processor systems, the work that's going on there. So Venkat, I'll turn it over to you now.
Thank you so much. Let me share my screen and go full screen. Can you see my slides? And is it in the presenter mode? Presentation mode. Yeah, perfect. Yep. Thank you so much.
Yes, sir. Yes, sir.
And thanks for the introduction. And I'm really happy to be here today and describe some of the efforts that we have at the Argonne Leadership Computing Facility on evaluating novel AI architectures and accelerators for scientific machine learning. So I'll start off by giving a brief overview of the Argonne Leadership Computing Facility, ALCF. We are a Department of Energy Office of Science user facility where we offer computing resources to the scientific community. We are one part of the DOE leadership system. Our sister facility is the Oak Ridge Leadership Computing Facility at Oak Ridge National Laboratory, and together we are part of the Leadership Computing Facility and Systems, where we offer time to the open science research, and the systems that we have are available through various allocations such as Insight, ALCC, and Director's Discretionary. I'm happy to talk about them. And the architectures are really pushing towards enabling science, which combines simulation, data, and learning on these really large-scale supercomputers. Okay. We have in-house experts that can have in-depth knowledge on various scientific domains, together with expertise in AI and data science, and we've worked with the open science community over here. Just to give you some perspective, we deployed the BlueGene-L system in 2004, and we had several deployments of the BlueGene systems, ranging from BlueGene P to BlueGene Q. And around 2017, we deployed a KNL-based supercomputer, which is the Theta system. And we added an A100-based partition to this. And we have been recently installing the Polaris system, which is an HPE AMD system, and it includes the A100 GPUs over here. And soon we'll be getting, we are already getting ready for our Aurora system, which will deliver over 2 exaflops. So as you can see, over the years, we have been deploying a number of systems, and these systems are getting, we're seeing very diverse signs, and the community of users that we run on these systems have really spanned across a wide number of domains. And what we are witnessing is a good surge of scientific machine learning to run on these systems at scale. And to just give you a perspective of scientific machine learning on these systems, they come in different flavors. In some case, teams are looking to either replace a part of the simulation with an AI-driven model. These are sometimes called surrogate models. In some cases, you really don't have a well-defined physics model that you're trying to replace. You're just trying to make sense of the data and build models. These good examples are, from what you know in connectomics, which is study of the brain, connectivity, among others. So you have very, very data-driven models, and you see good coupling of these as well, where you have well-known physics together with regions where you could, for example, in regions of turbulence in aircraft, where you could augment them with some data-driven models to really better design these or better model these scientific phenomena. We are increasingly seeing the use of AI for even steering these experiments or simulations, and a science campaign really combines them in very interesting ways to deploy, to get discoveries. And I'll be talking some of them. So you'll see good combinations of these that are needed to get real science done. And a key goal for us to really understand is, how do we effectively run these models on large supercomputers? At the same time, what we are witnessing is, the AI accelerator landscape has really grown over the years. And here's a picture from, some information from a couple of years ago, and this has really grown over this period of time. So there's a wide variety of accelerators that have really proven in terms of performance on enterprise workloads. And one of our key goals is to really understand what are the efficacy of these accelerators for scientific machine learning. Scientific machine learning workloads are very different. We have, data sets that are very complex, extremely high dimensional. They could have data models and shapes which are very different from what you might see in scientific machine learning, from traditional machine learning. You may have custom loss functions that would need to be defined. And the key goal is to really understand the efficacy of running scientific machine learning applications on a variety of these platforms, and evaluate the performance. There are some more additional elements that we are interested in, and specifically is, as you really think about the bigger picture, for example, thinking about Aurora, which is already designed, but we are looking forward into systems beyond Aurora. And the goal is, these supercomputers are going to be connected with a variety of experimental facilities where you can perform some of the near real-time or real-time analysis. Many of them are AI-driven on systems such as Aurora and others. You also have edge accelerators that are there for running inference, or it could be even online training. So if we have to couple these elements as part of our supercomputing design, what does it take? Another aspect that we really need to consider is if we have these innovative AI accelerators, how do they couple with systems? Are they part of the of a node on a supercomputer? Are they disaggregated where you have separate racks? Do you couple several of such chips either on a node or on separate racks where they're combined to the big system on over the network or the interconnect, together with how do you deploy some of the edge training or inference that you need to perform? So these are a variety of workloads that we need to investigate in addition to understanding the efficacy of scientific machine learning on these AI accelerators. So that's a big picture that that we are trying to tackle. And towards this, our goal is to evaluate, work with several AI vendors and really evaluate the performance of these accelerators for a wide variety of scientific workloads. And when we talk about evaluation, some of the key goals are to understand how mature are the software as well as the hardware to meet the needs of science. If it works on a couple of nodes, as you start scaling out, what kind of challenges are there? So what does it take to really integrate this with big facilities such as at ALCF? And finally, it's about how effective are these for real science? So we have established the ALCF AI testbed. There's a URL over here that you can go and visit. And as part of our testbed, we have a Cerebrus CS2 system, the Sambanova data scale. We have deployments from GraphCore, Habana, the Gaudi system, as well as the Grok accelerator. In addition, we are really working very closely with a wide number of other partners here, trying to really incorporate the testbeds. And we will be taking this testbed, making this public to the wider audience. So folks in attendance can actually go to an allocation page and apply for a director's discretionary allocation. I'll talk some about the process and procedures for that so that you can also get to evaluate your workloads on these systems. So it will be open to the wider audience here. And the key goal, again, is to really understand how these accelerators will influence the kind of systems we deploy going forward. So, just giving you a brief overview of the systems here. I'll actually drive home some of this with application examples and success stories that we have. Next, I'll be covering 2 applications as part of this. And I'll try to close out with several observations that we've made on early evaluations over here and conclude over here. So to just give you an overview, some of these architectures are very different from what you might see on a traditional GPU architecture. You have hardware, which is a data flow based, such as, or they combine some very large instruction words, so some other innovations that have been there, and several innovations are being made in a compiler so that you can take workloads and effectively map them onto these architectures. One thing to note is that the precision support on these systems are typically 16-bit, or some of them do support 32-bit operations. So another key aspect for us is to understand, the importance of using reduced precision for various scientific machine workloads. There are certain use cases where we do know that you need 128 bits. For example, in some of the work that's ongoing in, say, in lattice QCD. But for a wide variety of applications, we have seen effective use with 32-bit and 16-bit. So the question is also trying to understand the impact of this. And in many cases, these architectures have lots of custom secret sauce where they can increase the range and precision as well for these floating point numbers. One thing that you'll also notice is that the systems have really worked on how do you scale out. So they have custom interconnects that can be used to connect various chips to build larger scale systems. Many of them are proprietary or 100 gig E based. And we have seen them adopt the deep learning stack that's used to run scientific applications here. And I'll talk some more about the software stack. So if you think about what we have achieved is we've been able to run a wide number of scientific applications from a very diverse set on the system, ranging from the cancer drug response problem to imaging sciences to inference for understanding fusion reactor operations to protein folding. These are just a few examples, and I would say that if I take the number of use cases over here, this slide would be full of images, which is really good to see. So I'll be touching today on two applications. I'll be covering one on protein folding. This is related to some of the work that we've been doing in COVID-19 and how it's been able to use the Cerebrus CS1 and CS2 system successfully. More recently, we've been able to port this to run effectively on the GraphCore system as well as on the SambaNova system. And I'll also cover an imaging science example where the models and the image sizes are really large, and the large memory footprint that you get on these accelerators have been key to being able to run at native resolutions here. So the first example that I'm going to cover is on Stream AI MD. And in this case, our goal is to really understand protein-protein interactions. These have been used to understand various SARS-CoV-2 proteomics, among others. And the key goal here is to apply deep learning to steer the MD simulations to reduce time to solution for to understand the behavior of protein folding here. And the picture is a bit, I would say, has got too many details, but I'll try and explain in brief. And you can always go and read the paper, which is published at TACC 21 this past year, which describes this in detail. And the key insight is, you could take all the combinations of, protein-protein interactions that you want to see and do a large ab initio simulation. Or another way to really think about it is, based on some existing running simulations, can you really identify, instead of running the whole ensemble of simulations, can you adaptively sample these simulations so that you could better sample the conformational space for folding? So in this case, what we do is we start with a bunch of simulations. We generate a 2D contact matrix of them. That's step one. We take this and we feed it to a convolutional variational autoencoder, that's in 2. And we try to get a latent space representation, which tells us, have we seen this kind of trajectory or latent space before, or is it something, or is it, or are there any anomalous trajectories that we're seeing? And from there, we can really understand whether we should, stop the simulation and launch new configurations, or can we continue the simulation because it's a configuration that's providing new and unique results. So this is kind of the adaptive sampling or intelligent sampling that the efforts are underway. And I would say that this has been, since we've done this work, we've actually extended this to really couple together experimental data that we get from cryo-EM together with finite element simulations together and MD simulations, and able to stream and drive them together using AI. This was part of a recent Gordon Bell finalist paper, and I'll talk some more about it. So just to give you an insight on this, here is an approach where we're taking simulations and trying to couple it with AI, which is trying to understand the latent space representation, as well as trying to detect outliers, among others. And what we've done in this case is we run the simulations on the Theta GPU. This is a DGX3-based system where each node has 8 GPUs. And we have been able to couple this together with the, in this case, it was the CS1 system from Cerebrus. So we would take data from the Theta GPU, and we would stream the trajectories to the CS1 system. We would do online training. We would take the weights from there, send it back. We had reserved a GPU to do inference. We would stream the weights to the inference system, run inference to identify which simulations to continue, or which to stop, or which to seed again. So this was in early 2021. And since then, what we've been able to do is we've been able to modularize this. We can run the simulations on any system. We can run the AI training on any system as well. So we've been able to couple, it could be a GPU-based system, it could be a Cerebrus system, it could be a Sambanova system. And we are also being able to make this infrastructure distributed. So we have some new workflow innovations that we have done here, which are part of the 2021 Gordon Bell finalist paper. So just in terms of results, that if what we were able to do is we were able to compare the results that we get on the, if you were to just train it on the A100 versus training it on the CS1 in this case. And we were able to fit larger batch sizes as in comparison to the A100 in this case. And we were able to achieve close to a 3.7-fold speed up, just for training. I do have to point that we were training in mixed position on the CS1 while we were training in FP32 on the A100. So we actually saw a lower loss on A100, slightly lower than what we were achieving on the CS1. And this is for an older model, and there've been more innovations that I'll talk about since then. And from a science perspective, what we were able to do that, if you were just to take an ab initio simulation and ensemble simulation compared to this, an AI-driven approach where you could couple simulations and AI, we were able to achieve close to a 50x speed up, and an 8-hour experiment achieve a much lower root mean square error than what you could get with an ensemble equilibrium simulation. So that was a really key insight, where coupling these two together and using accelerators to reduce the time to solution for training proved to be very critical in this case. So having said that, as I mentioned, we've since that work, we've done additional work with the Cerebrus CS2 that we've deployed in-house. And here is a work, the same CVA model that we've scaled out on Summit and compared the performance of running this on Summit versus running it on a CS2. And what's really novel is, out of the box, we are able to achieve close to 100x improvement over what you would run on a GPU on Summit. Summit gives you the scale of the system, so you could really scale out on these systems. And if you just compare the improvement that you get running on a CS2 with a V100 or running a CS2 on a A100 right out of the box, you get a significant improvement. So in comparison with the with the V100, you get up to 100x. In comparison with the A100, you get from a 20x to a 32x. The 523 by 523 or 926 by 926 are two different residues, so two different problem sizes. And for both of them, you see a significant improvement and speed up in comparison to what you can do on a GPU-based system. There are more details in the paper, and I'm happy to answer more questions later as well on this. So that was one use case. Another use case is with the cosmic tagger, which is a very important application in neutrino physics. And in this case, we're looking at image segmentation. And one of the key challenges in this application was that, given the size of images and the model size, we had to really downsize the images to make it run on and fit on existing GPUs, such as even the V100 or A100. And we could take close to the native resolution or larger images, I would say, and run on systems such as the SambaNova in this case. And this just provides you some information on, by using some of these accelerators and the memory footprint that they provide, you're able to run larger models, and where you can get even improved accuracy and performance over here. And there are more results in the paper that I have listed here. So I talked about the discretionary allocation for getting access to the AI testbed. Here's a link that you can go and visit. And as I mentioned, we are opening up the testbed, taking the Cerebrus and the SambaNova system live first. And this is expected in the next month. So please to visit the site or send me an email, and I'm happy to help you out there. So some observations that I would say is that, it's not all rosy. The software stack on these systems are very catered to, a few models. Whereas I would say that if you look at the software stack on systems such as on GPUs, they support a wider class of models. And that's expected because these are startups with limited development resources, and they've worked very closely with us across the board to port and support existing models. So different vendors support different frameworks. As an example, you have more improved support for PyTorch on SambaNova and TensorFlow on Cerebrus. Cerebrus is starting to support PyTorch as well now going forward. So there is, if you compare them with what's supported on other platforms, it's definitely not all operators and models are supported, but they are making good leaps and bounds improvements to facilitate larger models here, and a wider range of it. You do need some porting needs. Our hope is that a model can just run out of box. You do have to put some time and effort to run on these systems, and it differs based on the system on which on where you need more effort, whereas in some cases a minimal effort is needed to run on them. I would say that there is more work that's needed in terms of tools such as profilers and debuggers to really inspect and understand why exactly is a model performing it the way it does on these systems. Vendors are putting effort into this, and I've seen improvements over the interactions with them. But I'd say overall, we've seen really good, promising performance for several scientific machine learning applications, both in terms of scaling, as well as in low batch or batch one inference modes as well. Yeah. So in conclusion, I'll say that we've been able to really port and get good performance for scientific machine learning applications on a variety of systems such as Cerebrus, GraphCore, Grok, Habana, and Sabonova, and good improvements when you compare to GPUs. And this is an active work where you have to engage with application teams to help them run and scale codes on the testbed. And this is something that vendors have been working closely with us, and as we open up the test beds, we'll be working with a wider community as well. So with that, I'll acknowledge the funding for which is from the Department of Energy, this is the work of several folks, and I'm just representing them. So with that, I'll say thank you for the time, and happy to take any questions you may have here.
Venkat, thank you very much. That was a fascinating discussion. I want to stay on schedule, but I did want to selfishly ask at least one question. NVIDIA had their big GTC conference this week, and Jensen came out and talked about some very impressive capabilities in terms of what they're calling a super pod, basically a 50 plus exaflop AI supercomputer. And my first thought was, is there a need for this? Are people computationally bound at this point to that degree where that kind of system of that size and capability will have wide usage, or is it I don't want to say a stud machine, but is it something that has the potential for this scale but may not ever actually be needed by more than perhaps a small number of users?
Oh, a great question. So let me give you a couple examples. So we work very closely with the connectomics folks. They collect data from electron microscopy, and they are trying to understand the human brain, aging, Alzheimer's, among others. So if you take the resolution of data that they're collecting for a mouse brain, and it's in the close to, and you start projecting on kind of the needs of computing that you would do as you're planning for a human brain, our initial projections were that to solve some of the, I would say, medium-sized problems in this domain, you would need to run a dedicated AI problem for 3 years on an exascale system to get the insights that you need. Mm-hmm. And the scale of problems that they have are much larger there. In the COVID-19 work, you're looking at really small problems right now in the, I would say, 1 million range. We have to really hit the 1 billion plus range, and the problem sizes really become larger. So as part of our the Aurora early science program is for interesting science problems that can fully utilize an exascale system. And we have 10 science problems or 10 science projects spanning data and learning and AI that couples simulations as well as AI in most cases that really need the scale of exascale systems. So, I would say that there's also a reason why NVIDIA and Jensen are manufacturing this, or if there wasn't a really market pull or a need as you made it, they wouldn't be really investing in that. So there are science use cases that will really utilize systems such as these.
Great, cool. Thank you very much. Appreciate it. That was a fascinating discussion. So we're gonna move right along just to stay on schedule. One of the things that I think some people who look at the sector don't fully understand is that right now there are many different ways to establish the quantum phenomena to do qubit-like calculations. There's things like superconducting qubits, trapped ions, photonics, NV centers. It hasn't settled down yet. There are challenges and opportunities of each of these so-called quantum modalities that exist, and so I'm particularly pleased that we're able to corral Stef Simmons from Photonic. She's the chief quantum officer there, to give us a quantum technology update and give us a little bit of a flavor of what's going on at Photonics as well, hopefully. But Stephanie, thanks for joining us today. We really appreciate it.
Well, thank you very much. And unfortunately, no, you're not going to get very much from me about what's happening behind the scenes here, but I can give you a snapshot of the whole race. We are still in stealth mode largely, but I can absolutely give you a flavor for what's coming.
Cool.
So if you would permit me, I'm going to share some slides. Right. So this is the most exciting it's been. It just keeps getting more and more exciting in the quantum space. I've been in quantum since basically I was 16. Quantum technologies have been my whole life, and I'm really excited to see how quickly things are moving and how well it's going. So thank you very much for your interest. It's great that it's no longer something owned by academics, as it were. It is definitely going through the spin out and the mass proliferation of startups phase. There will be a dominant design when it emerges that Bob was alluding to, and then there's going to be a consolidation and a talent scramble, and we've seen this before. So let's go back and think really big picture here. If you go and you take a look at the major events that went through the kind of gradually then suddenly, right? Major technology shifts over the past, couple hundred years for human history or longer. And you link it back, most of them, although not all of them, but most of the major ones can be anchored in essentially the commercialization of a branch of physics, right? So, I mean, I didn't make this plot, I just pulled it off the internet, but you can actually point to the advent of, say, semiconductor physics, which gave rise to our understanding of silicon, which allows for all of the communications we can have today and the supercomputing processor we have in our pockets. There's a lot of physics that enables it. And so you can use this as you can't necessarily predict the details of what this unleashing is going to be, but you can draw from those experiences and say, quantum technologies are the next one. We know what roughly we think they're going to look like, but you have no idea how big it's going to go and how quickly it's going to go. Most of these things did have that kind of hockey stick curve to them. And you can use semiconductor physics as an example, right? Because the major use case that was identified before semiconductor physics, like transistors, really took off, was a hearing aid, right? It was the fact that you can maybe miniaturize what used to be done with valves, right? Like big vacuum tube valves. You can miniaturize it and get hearing aids working. So that was the use case that was identified there. And we're in the same kind of situation we are with quantum right now. It's actually kind of fantastic that we have predictions of what kind of things we're going to be able to unlock, like just ways that you can't do it any other way by using quantum technologies. And this is, again, before we get the really large systems up and running. So I'm really grateful to the previous speaker for outlining a lot of this stuff. So forgive me if I'm going to be going kind of back to the basics a little bit and rehashing it, but maybe it'll give you a slightly different view on this and why it's important. So the main fundamental difference between quantum tech and classical, it's not just classical computing but faster. It's a completely different way of processing information. And we have no better word to use than computing to describe that. but it's completely fundamentally different. And so the one thing I would emphasize is as we go through this upcoming hockey stick transition, which is coming, there is going to be a massive talent shortage, and there already is. So I echo the concepts given, or the statements of the previous speaker, that really getting early is the only way you're going to survive this, because the talent scramble is going to be crazy, because it's just processing information differently. And why? Well, information is ultimately physical. Like, we like to think of information as this digital, like gaseous thing, right? Like the gaseous thing that just kind of like transmits. But that's not how it is at all. It actually is represented in physical, little mini magnets, for lack of a better term, within semiconductor material, right? It's a physical switch that goes and it stores a 1 or a 0, and you can process that 1 or that 0 according to the laws of essentially what we've been using so far as classical physics. So forgive me for calling traditional computing that everyone's aware of as classical computing. It's because it's using the laws of classical physics, but ultimately quantum physics is richer. You have more, you can do more if you use all of the laws of quantum physics, as opposed to the restricted class of physics, which is available for classical systems or large scale warm systems typically. So here, visually, what I mean, there's a lot of math backing it up. And the math is a lot of matrices. So that's the natural language of quantum systems, as it were. But instead of matrices, I'll show you kind of I'm trying to give you a diagram of like why quantum is going to completely change the way you think about things when it's at scale. And especially information processing at scale. So instead of the digital 0 and 1, where it's like a light switch, right? It's a 1 or a 0. Quantum information, and this is true for all objects that are well treated enough, they can exist in superposition. They can exist in some sense 0 and 1 at the same time. And you can represent, it's not just 0, 1, or maybe, it actually is a full infinite set of possibilities in terms of superposition. So one way of representing that is with color, right? So you could say it could be any color in that continuum, any shade as well, right? So 1 qubit is with 0 or 1 when you measure it, but it's anything in between, and that is infinite ability to hold information. And the way that you add quantum systems is really where you get this exponential power for some things, right? So I'll give you a diagram, and again, forgive me if it's a little bit cartoony, but I'm just trying to paint the picture for what's coming. So we have classical computing is truly a subset of what you can do with full quantum systems. And we've been very, very capable with the classical things that we've done so far. But there are some problems you don't even try to do because it's just so far beyond scope that you wouldn't even try. And simulating, we'll get to the examples in a case, but notoriously simulating quantum systems themselves are way in this category, right? It's just, there's too much information possessed in chemicals for us to simulate them properly in a computer. And so visually, what are we looking at here? So a classical computer, let's say you have 8 bits, 8 classical bits. It could be in some 00000 state or 1100 kind of state, right? Like, so it could be any one of the dots on this one line here. So this is just to be a visual to try and show you what quantum can do, what it can hold. So today's code, if you're going to go using those 8 bits, you're actually just going to be flipping around one black dot on that line. So their quantum systems can explore this whole space. And this is just for 8 qubits. If you put a 9th qubit, it quadruples the size of this diagram. So the scaling is where you get this gain, right? So there are annealing systems. D-Wave is the only main manufacturer for annealing systems. They are also based here in Vancouver, right down the hill. They are not universal. And what I mean by universal is they can't do everything quantum can do, right? The full scope of what quantum can do is truly every color on every pixel, right? You can technically create these states and encapsulate all that information in an 8 qubit state, right? The power is just enormous. You can encode a whole human genome in 30 qubits. And I think the number is 270. If you have 270 qubits, it would take more classical bits than there are atoms in the universe to encode that state, right? So it's just the capacity of this stuff, the information capacity is really where you're going to get these gains. But you'll note all of these algorithms here, they end with a black dot. And that's because when you measure it, you're measuring it, you're forcing it into a classical result, right? And so the kinds of algorithms, the kinds of questions you can ask it when you're expecting a classical result at the end are ones that have very succinct answers, right? So you're not it's not necessarily a high data kind of environment. You're looking for a needle in a haystack kind of problems, right? Like, what is the solution to this very, very complicated problem? And so I can give you a whole bunch of examples for that. There is a place, and if you're mathematically inclined, so for those of you in the audience who are mathematically inclined and are just getting into the space, I would recommend quantumalgorithmzoo.org. They maintain the list of the mathematical algorithms that have been derived pen and paper, right? So again, we don't have these things at scale yet, but these have been derived pen and paper that have proven exponential speedups over the best known classical algorithm alternative. And I'm just going to shout out 3 here because these I think will be the most impactful for us collectively over the near term. But again, these are kind of the hearing aid applications. We have no idea what the Facebook equivalent would be from when we finally take this physics and commercialize it for a few decades, right? So this is just what we know now because we don't have an actual system yet to test on the heuristics. One thing I'm not going to mention on this slide, but I'll say it here. There's a big unanswered question as to whether or not machine learning, how much better it's going to be with quantum. For those of you who have done machine learning, matrices are the name of the game there, right? So you'd think that quantum has a really, really natural leg up, and it might, but there's a lot of work that's being done to figure out exactly what that speed up could or might or would look like. The difficulty with machine learning is, of course, a lot of those are heuristics. They just seem to work rather than they've been, from an algorithmic complexity perspective, proven to be better than anything else. So there's a lot to be figured out there, but let's just talk about the ones where we know that there's an exponential speed up, right? So the chemical simulations, huge, right? Material simulations, chemical simulations, this is the natural language of those systems. And if you want to figure out better catalysts, better molecular docking for drug discovery, if you want to just figure out ground energies, you're going to need a lot of qubits. Not going to deny it, but there's no other way to hack those problems, right? There's no other way to efficiently go at those kinds of problems, especially if you're looking for heavy chemicals, right? Like heavy atoms. I think this is going to be the only way, and it's going to really change the entire way we think about drugs because it's going to be finally done computationally rather than with heuristics. Pharmaceuticals, that whole sector is going to be completely quantum. It's going to be completely quantum, and we should get ready so that we can have milestones for what to deliver when the certain number of logical qubits come available, and I'll get to that in a bit. The second one is quantum communications, and this one, and I don't mean to be a bit of a fear monger, but there's a lot of recent news in this space, and I want to just bring it to your attention. So the third element here that I'm going to speak to is the fact that quantum computers will be able to break RSA encryption. This is the backbone of most communication that we have on the internet. And at the moment, there's networks of quantum systems that are going to be able to offer unhackable communications. They already can. So this middle figure here is what I'm trying to demonstrate, is that there is an ability to secure communications using provably secure physics as opposed to computationally secure. So what do I mean by that? Right now, when we encrypt our information, we're relying upon math that we just assume is hard, essentially. And it's hard for a computer to figure out, but it is the case for quantum systems. They are able to efficiently figure out the answer to those challenges. Now, computationally, that's, there's a lot of work that's being done for people to figure out if there's another computational problem that will not be possible to attack with a quantum computer. People are really trying to figure this out. They've been trying to figure this out for a while. So there's three instances in the past, which I am aware of now, where the world decided, okay, this will be an algorithm that replaces RSA and will be secure against future quantum computers. It was Diffie-Hellman, Soliloquy, and then most recently, I think it was like 2 weeks ago, one of the short lists from NIST was Rainbow. They've all been hacked. They've all since completely fallen apart. So it's a really unclear what kind of computational security is going to be able to exist once quantum computers boot up. But there is quantum physical communication security. So it's relying upon the laws of physics it's basically no cloning principle. Like these are just laws of physics in quantum physics that allow for unhackable unhackable communications. Or rather, if it's hacked, right? So you can't eavesdrop it, and therefore you can ensure that when the link exists, it's secure. They exist. You can buy these things. QKD is one of the acronyms you can go look up if you're interested. But this is a major issue because as soon as a quantum computer gets booted up, all of the modern encryption is going to be a lot of people right now believe that most communications, most secure, high value communications are being saved right now against future quantum attacks. So I would highly recommend taking a look in terms of critical infrastructure, securing that in a way where you're not relying on RSA. But if one thing to do is that you can use QKD, if you can consider QKD or other alternatives to secure that communication. I think that's going to be the one wake up moment when the whole world realizes, oh, quantum's really here now. So there's that. And then, yeah, the third item here was encryption breaking. So those are the three most major that I think I would bring to the attention of this audience, beyond machine learning. And then the fourth one is connected to this kind of distributed quantum challenge. This is to do with sensing. So I think there's, again, the laws of physics are different. So computationally, you get these gains when you combine systems, they grow exponentially. So you get these exponential speed ups. But you also get other laws of physics. No cloning allows for this physical security of communications, but you get like better sensing capabilities. So the correlations you get between quantum systems are just inherently far, far more sensitive. And so depending upon what you're trying to sense, quantum systems might be the solution. There's definitely magnetic sensors, electromagnetic, electric field sensors, strain sensors. They don't all operate in all conditions, but go take a look. If sensing is the name of the game for you and your business, quantum sensors are booting up right now, and they don't need large systems necessarily to offer commercial value. I would say, yeah, there's lots of early adopters in this space, and we've heard about a few of them. But yeah, I think the general point is here, if you're waiting for 100 logical qubits to get involved, by that point, the talent will be completely bought up, and the gains to the early adopters, I think, will be formidable. So if you're interested in engaging, please do so. It doesn't have to be us, right? There's lots of different people you can go to, but training a workforce, I think, will allow for a more efficient transition and less jarring for everybody. Now, okay, what will quantum computers not do? I don't think out of the gate, they're going to be better at helping you stream Netflix, for example, right? I don't think actually they're going to help you make a better calculator. One of the things that quantum computers are particularly bad at is straight up addition and division, right? So they're good at their thing, right? It's a complete, as I'm trying to say, it's a completely different branch of physics that's being commercialized. These will be co-processors. In kind of the best case, the classical quantum feedback is going to be really important. And there will be things that classical computing is just better at. So it's not going to necessarily replace the infrastructure you have on your desk, but it might be connected to the infrastructure you have at your desk for, say, communication purposes or similar, right? So there's a lot of things that quantum computers are not good at. So it's not going to go and take over all of computing. It's going to do what the plane did to the car, right? When the plane came, people didn't stop driving cars, right? But it did open up a whole new world of possibilities for lots of people. So that's more the way to think about it. It offers new capabilities that can't be done any other way, but I don't think it obviates the phenomenal computational power that we get when we use classical physics. So I have a few minutes to kind of indicate the current state of the race. Why has the world really taken notice over the past couple of years? I think the thing that really caught everyone's attention first was the quantum advantage demonstration from Google in 2019. This was the first, I would say, quote unquote, hello world algorithm where I mean, it's more than that. They demonstrated something that couldn't be done using classical computers in any reasonable time frame. And when we talk about a quantum advantage, it's not the absolute ratio. So for example, they used 53 qubits and they claimed that the best case that you could use classically was 10,000 years. And they took, I don't know, I forget how long it took, maybe a couple minutes or something. It was reasonable timescales compared to 10,000 years, right? So it's not the ratio that matters, and you'll see this in other suppliers. It's the scaling, right? So it's the fact that if you added another qubit, it would take 100,000 years, but it would only take, you know, an extra n+1 amount of difficulty for a quantum system, right? So it's the scaling that really matters rather than the absolute ratio. But of course, the scaling is what's going to give you better and better ratios as these systems get larger and larger. China caught up pretty quick. So in 2020, they did a all optical version of this. So it's a very interesting race, but I wouldn't say that necessarily there is consensus around what the hardware will be to unlock something truly scalable. I have my views, other people have their views. I'm not going to talk about our technology, although I'm certainly happy to be working where I am, but I will happily tell you the roadmaps that have been discussed openly by our competitors. And so these are different platforms, different physical things. I mean, technically a popsicle is a quantum bit, but it's just a really bad one. So there are lots of metrics beyond just count. I don't think count is really the way to be thinking about it, but it is what people are using as a marketing tool. So I will absolutely point to it. So IBM and Rigetti are different kinds of so-called superconducting systems. These need to work at millikelvin, like fractions of a degree above absolute zero. They have very complicated systems. I've engineered on that side of the fence. We don't have to work at those cold temperatures, but that's their systems. Google also uses that same kind of technology, similar. Cold quanta is a different kind of technology. It's doing trapped atoms in a lattice. IonQ is trapped ions. So again, like this beautiful old physics demonstrations that are being used for computational purposes. Most of these have a box, right? So IBM is, you know, the size, it has like, it can probably get about 1,000 qubits within one box. And that's why you can see here that they kind of sit at 1,000 for a while, and then they promise the world. You can get, Rigetti's in a similar position. They're not promising anything before they get this kind of, the ability to link boxes, essentially. Cold quanta is in the same kind of game. That's the max size for their unit. We are, and same thing for IonQ, their box size, as it were, for per module is on the order of much smaller, a couple dozen. But the interconnects between boxes enable true long distance scaling, and that's what we're focused on. PsiQuantum is a bit different. They're most closely related to us. They are a pure photonic play. Whereas we have spins and photons in our technology. And so PsiQuantum has claimed that they're going to start building their 1 million qubit system in 2025. Now, what do you actually need? At the moment, the dominant view in the literature is that you need about 1,000 physical qubits in the best case for one logical qubit, right? And you'll see different numbers depending upon, you know, there's a lot of things that feed into that number, but it's somewhere between 1,000 and 10,000 physical qubits for one logical. There have been, just to put on your roadmap, on your radar, there's a lot of work on making better codes. There's a lot of work it's very exciting, making better and better codes that we're going to change that ratio completely. So I wouldn't say that this is, I think it's going to be a hockey stick event, and a lot's going to come all at the same time. So it's quite the wild ride, I would say. Now, so this is just kind of lay out the Google map, what that means. What's the difference between so-called NISQ and error correction? This is an old figure now. The question is, how many logical qubits do you need, and what ratio do you get to physical? There are absolutely things that people are doing now in NISQ, right? So NISQ is noisy intermediate scale quantum. It's where you're playing with just the physical qubits. It's what some of the VQE algorithms that we heard about in the previous talk, QAOA, these kinds of algorithms are trying to make use of quantum systems before they have that physical scale sufficient to do logical operations. But I would argue that actually there's a lot of work to be done on what are the most valuable things we could do with 50 logical qubits or with 100 logical qubits. Like what does the logical qubit roadmap look like? And have people continue to work on those overheads, But what's the roadmap on the logical side? Because that's where we're going to really unlock value. That's where these systems do what we want them to do, as opposed to noisy and degrade over time, right? So I would argue that there's a lot of work, because in the commercial side, people are trying to make money now, and you can't blame them. But that means they're trying to make money on these NISQ systems, and that's almost at the expense of developing the logical qubit algorithms needed to extract value as that roadmap boots up. As we have more and more logical qubits coming online, it would be great to have an agreed upon commercialization path for all of these different verticals, so we can extract value as these things come up. So there's it's not, so what this graph is trying to show here, is that there exists an error correction threshold. So it's not just about sheer number. And this is what I was getting at on the previous slide. It's not just about sheer number of physical qubits. The quality of the qubits needs to be sufficiently high to do error correction as well. And so it's the quality of the error, there's a whole bunch of different parameters for that. So forgive me for not, well, I'm not going to bore you with all the details, but the comparisons between all of these things, there are many different ways of comparing these different systems. And ultimately, it's going to come down to who can deliver the logical qubits first, I think, and what you do with them when they do get booted up. So keen to engage on all kinds of things with those of you around the table if you're interested. One thing I would just say is, again, you can start to see the hockey stick going on the investment front at a minimum. Again, this is partly to do with the fact that we've demonstrated quantum algorithms now that completely surpass anything. I mean, that algorithm was useless, the one that Google and China chose. They were commercially useless, but they showed what's coming. Investment has gone nuts. Now I know investment's gone nuts across many different sectors last year, but last year it was just 4 companies have pulled over $2 billion, and even last week we heard another spin out from Google, a quantum spin out that raised over $1 billion, right? And that's just from like last week. This is going to be a big talent scramble, so getting engaged I think could be helpful. So yeah, that's our team. Thank you very much for your attention. I hope we have a few minutes for questions.
Hey, Stephanie, great. Thanks. That was really a fascinating tour there. Enjoyed it greatly. Again, I'm looking for questions. People can interrupt me when possible, but again, moderator's prerogative here. Since you brought up semiconductor device physics, one of the big transitions in the world that got us to where we are today wasn't the invention of the transistor. It was this transition from discrete transistors to monolithic integrated circuits. And that's what drove scaling.
Yeah.
So the question becomes, are we in the discrete transistor range, or are we in monolithic integrated circuit range, where the technologies today can scale to appropriate qubit size to deal with error correction overhead and such? Or are we going to have to go through another turn of the crank to ensure that we have technologies and modalities that scale beyond, say, 1,000 qubits on a single unit?
Yeah, so it's a great question. I would say there's different challenges for generation 1 and generation 2 quantum technologies. So generation 1 quantum technologies were the ones that were known to the world back when quantum information started off, let's say in the mid-90s. Those ones have different, they had early capabilities, and so they were great demonstrators, but they were much more in that kind of individual transistor, to use your term there. They're individual components, small number of systems. I think the name of the game is going to be distributed computing, just like it is for classical computing. It's going to be about distributed quantum computing rather than monolithic quantum supercomputers. As things move on, they'll get more and more integrated. But yeah, I think there's fewer challenges ahead for the generation 2 quantum technologies, which have photonic interconnects essentially.
Mm-hmm. Great, cool. All right, we have a question. Michael Bain, do you want to ask your question directly? Or are you struggling to get the mute button turned off? Okay, his question was, power consumption of a quantum computing capability compared to HPC to solve a given problem. you have any sense of power consumption comparison?
Yeah. So the marginal power consumption of a qubit is very low, but each system, depending upon what you're working with, which kind of physical system you're working with, something like 10 kilowatts. So, it can be quite a bit, but that's mainly to cool it down, right? For a lot of these systems, it's to get down to some base temperature. And then the marginal cost of each qubit on top of that isn't usually that high if you've engineered your system well. But the systems are very, very different, right? Like it's going to be very different power consumption for ion traps. They have to be in ultra high vacuum, so it's a different challenge, right? But from a high power, like the Google systems, those are going to draw a lot more, right? Those are cooler systems. It hasn't really been nailed down yet. The people are really working with whatever energy costs they can. It's really about what's physically possible from a scaling perspective. They haven't been working about size, weight, and power yet.
But that'll almost be more of a fixed cost for power. Even as you add more qubits, it's not going to scale like going out to 50,000 node system.
Well, sure, exactly. So it'll be a power per whatever box size is. So if your box is 1,000 qubits, then you have to, and you have high overheads, then yeah, you'll have to pay per box. But yeah, it's not with it. It wouldn't necessarily make the extra qubit within your system that much more expensive. Right.
Okay. Cool. Great. Thank you very much. Well, I think in the DNA compute and storage field, a very fascinating and interesting emerging technology that offers an awful lot of promise going forward. So Dave, we're going to turn it over to you now, and you can fire away.
Great, thank you. Okay, everybody see my screen?
It looks good.
Okay, cool. So this will be a little different, I'm sure, for some of you. Catalog is a startup in Boston, founded by a couple of people who went through MIT. And we're focused on building the first DNA-based storage and computing platform. My presentation today will take you into that a little bit, but I'm also going to provide you some background information in this that you can look at your leisure as well. So if we can just get this to advance, we'll be in good shape. Here we go. Okay, so a little historical background. Remember the history of Watson and Crick, and now look at the date on the lower left-hand corner, 1964. From the very earliest days, people began to consider the potential use of DNA for storing data. As far as we can tell, the first example of that, depicted on the right, was by Joe Davis, again with a couple of MIT players, who synthesized an 18 base pair message representing this Germanic rune on the left-hand side, and transformed it into E. coli. So 1988, okay? And I'm not going to go through this, but this will be part of the presentation you can look at your leisure. It just gives a list of papers and authors over the course of time that will help give you a perspective of what's going on, including some commercial enterprises as well, okay? Again, a little bit more background information that you can look at your leisure. Okay, so what do people mean when they talk about encoding data into DNA? Well, we make some observations first. DNA has been around for a long time. It is de facto a repository for information, otherwise none of us would be here. So it contains biological information. And so people have been playing with this idea now for about 30 years to see what else can be done with this. So the conventional way that people think about this is to look at the bases in the form DNA. So on the right-hand side of this chart, for example, you see ATCG, and it's simply reordering of those bases that constitutes the difference between one molecule of DNA from another. And it was very evocative to the early people doing research in this area that they could simply pair 2-bit values to each of those bases and then synthetically try to create a DNA molecule that represented the values in the bit stream they were trying to represent. So in the example here, we have 00001001111, And if you look at on the right, you can decode the colors on the left to the bases on the right, and you can see how that's representative of a particular bit stream. Order is important here because that tells you where in the bit stream you are. And of course, this dual bit representation to each base is critical to what's going on. Now, why do you want to do this? Well, if you're able to do this, you can store an immense amount of information in a very, very, very small space. So you could conceptually take all the information that exists on the planet and you could put it into something, I don't know, maybe order of magnitude of a coffee cup or something like that with DNA. So attractive first principles. But it has other interesting features as well. One is DNA is pretty robust as a molecule. It can last for a long time. We know this because we learned all of our science from Jurassic Park. So there's that history as well. But I think there are a couple of more interesting things here as well. One is it doesn't become obsolete. So if, for example, you were able to successfully encode data into DNA, it would create quite a different circumstance than what you have today, for example, with tape-based technology. So today, I think state-of-the-art is LTO-9, which implies that there was an LTO-8 and a 7 and a 6 and so on and so forth. And as I think you all generally know, that the evolution of technological transformation in the electronic industry typically involves some sort of rip and replace along the way. With DNA, a molecule of DNA encoded in 2022 will be readable by the tools that are available in 3022 or 30,022 and so on and so forth. So it allows you to escape that sort of upgrade phenomenon. It's characteristic of the electronics industry. And so there you go. You've got some motivations for why you want to do this. Now, the problem is that conventional way of encoding data into DNA carries with it a rather substantial cost. And the cost is that every time you try to add another base on the left-hand side, it takes you about maybe 30 seconds or so. So immediately you can observe that using the tools of molecular biology to create synthetic molecules, it might take you an extraordinarily long time to encode a fairly modest amount of data. Catalog from the very beginning conceptualized our company as a computer company. And the paradigm that we like to introduce here is this notion of movable type. And this is not Gutenberg because the Koreans predated Gutenberg and my CEO is a Korean, so therefore. But if you think about movable type, what does it consist of? It consists of an alphabet, if you will, and it consists of a set of rules of how that alphabet can be organized. And by virtue of that organization, you can convey value in the form of words to a sequence of members of your alphabet that are depicted in the movable type. The advantage to us of that, if we're able to do that, is it presents opportunities for automation, to operate at scale, and to reduce costs and size quite dramatically from the conventional benchtop chemistry approaches that have inspired most of DNA encoding to this point in time. So what's our alphabet? Our alphabet consists of oligonucleotides. These are small snippets of DNA, 20, 25, 30 base pairs in length. Human DNA is about 3.5 billion base pairs in length, so you can see that it's quite small. We design these for a bunch of reasons, which I'll get to in a minute, and we can get them manufactured in bulk at low cost. So our alphabet is capable of being manufactured on our behalf at low cost. We've outsourced the chemistry, in other words. And what's the scheme that we use? Well, the scheme is combinatoric organization of these oligonucleotides. And that organization invokes a process called ligation, which you can think of as a stitching together of these molecules. Okay. A useful metaphor, by the way, which I sometimes use to help people understand this, is Legos. So if you were in a dark room and you had a bag of Legos and they were all the same size, you could reach into the bag and you could pull out pieces or Lego pieces and attach them one to the other. That's the way they work. and you'd create a stack. And if you turn the lights on, Legos typically come in a lot of different colors. Even though you might have stacks of the same size, same length, you would be able to distinguish them because there would be a different order of colors, most likely. So you'd have a stack of red, yellow, green, blue, black, and the next one might be orange, yellow, red, green, white, something like that. And by virtue of that, you could tell the two apart. That's a powerful idea in terms of encoding schemes that involve combinatorics, as I'll demonstrate in a minute. So what we do is essentially that. We have an alphabet composed of, you can see these multicolored pieces here. Each changing color represents the addition of a new oligonucleotide. So you see a lot of different colors represented here. And by virtue of doing that, you can create a quite substantial number of unique longer molecules. And I'll just reiterate one more thing before I go any further. Everything we do is synthetic. So this is not harvesting DNA from a living organism, nor is it using a living organism in any way to carry the DNA. Everything is done in the laboratory. Okay, so what's the model here? So we've conceptualized a DNA data structure that looks like this tree. And you can see that from the apex down, there's a dual branch at each node of the tree. And this corresponds in our language to a tree that's formed of 5 different layers. Each of those layers presents the opportunity to fork to accept one oligonucleotide or another one. And in this particular case, in the box on the left, each layer contains 2 oligonucleotides. They differ in color, and in fact, they differ in colors between the layers. So red in layer 1 is not the same as red in layer 2. So just keep that in the back of your mind. But when you look at this then, as you traverse this graph from top to bottom, you can see that you're going through 5 layers. And if you go all the way to the left, it's red, 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 red. And that corresponds to the number, the rank 0, 1. And then if you deviate on the last layer and go to blue, that gives you rank 0, 2. And what that does in turn is it lets you conceptualize the creation of a longer molecule of DNA composed of the piece parts that occupy each layer. And here's an example of how with 5 layers, you can create 32 different unique molecules. Okay. And in fact, what we do at Catalog is if the value of the molecule is meant to represent a bit value of 1, we build the molecule, and if it doesn't, it's assumed to be 0, and we don't build the molecule. So this is an example here of how we take this sort of data encoding scheme shown up above and ratchet it all the way down to the bottom to map data values in a bit stream by location to the construction of a molecule represented above. Okay, so, and this scales exponentially. So if you have L layers of N components, we get into the L bits of information with only Ln pieces of DNA. Our library is about 144 oligonucleotides. That's more than enough for us to handle a terabit of unique information, i.e. a terabit of unique molecules. Now, to explore this phenomenon, we designed the machine. This exists in our laboratory in Boston. It's composed of several parts that are highlighted here, 4 main parts. There's webbing that goes through the machine, sort of evocative of classic computer tape, but much wider and different in a lot of other respects. And so you read this chart from left to right. It goes underneath a print engine, which contains a substantial number of inkjet printheads off the shelf. Those in turn are connected to bags of DNA-infused ink that you can't see in this particular picture. And then under software control, we can orchestrate the deposit of ink droplets with unique pieces of DNA on this webbing in real time. The webbing moves through at about 16 meters a minute. And we actually do 500,000 deposits of DNA per second on the webbing. you make a right hand turn into an incubator to let the chemical reactions take place, where the pieces of DNA that we presented in the print engine part of this cartoon are brought together and ligate or made to connect to one another. And then it finally ends up over on the right where it goes into a pooler where the chemical reactions stop and the DNA is removed for further processing, which could either be storage or something else. Now, this is not a product. This is a machine we built to help ourselves understand the limits of technology and to explore what the consequences were of trying to do things at scale that no one's really contemplated before. And currently this is running about 18 megabits a second, easy enough to understand how this gets to gigabits a second and beyond. The other thing I'll say is that we know how to reduce the size of this machine effectively to desktop. So there's engineering, there's science, there's a lot of other things that go into that, but this is not the form factor that anyone would see in the wild, if you will, but it's what we're using right now as an instrument of discovery. These are the droplets that get produced. Each one of these droplets is formed by as many as 16 different droplets from the inkjet print heads, each droplet containing a unique piece of DNA. So there's overprinting here. There's additional droplets produced for the sake of error correction as well. As I said, we do about 500,000 of these per second. And this is just a little video depicting the machine in operation from the incubator forward. So what you're seeing is the polyester material going underneath. The yellow squares are simply a dye we put on it to make sure that we're observing that DNA has been deposited. And then it comes off to the end where the chemical processes are stopped chemically, and the DNA is removed from the webbing for future processing. So that's how that works. Okay, so now that you have that kind of in your mind, what can you do with this stuff? Well, you know, we start on the left on this chart with an identifier library. I can replicate this very cheaply. So if I've got one and you want 1 million of something, cheap, easy, quick. If you want 10 million, if you want 10 billion, if you want 10 trillion, it's all pretty easy and pretty cheap. I can also do selections down in the bottom. These are crude kinds of actions that can be done against this. So I can begin to select out of my library by depicting, let's say, criteria represented in each of the layers here, red in the first one, blue in the second, blue in the third. And by virtue of that, do a de facto sort through my identifier library to produce two outcomes that I'm looking for on the right-hand side. And then one can begin to use these different kinds of schemes to constrain the combinatoric domain of investigation. And just by choosing the paths and setting the rules in place for how to do that, one can begin to carve down and eventually find what you're looking for. There are a lot of different ways in which you can represent data here. It's not just a single kind of model that's represented, so various forms can be done. And things start to get interesting because you can begin to look at this combinatoric representation and you can begin to play with it in interesting ways. This happens to be an example of one-hot encoding, so which is sometimes used in machine learning and other kinds of applications. But you see the graph depicted as a composition of keys and data. And that in turn is used to take a conventional binary representation of data that you see down below and actually represent that with one molecule at a time in each of these so-called words that you see composing the graph at large. So you can begin to contemplate things like this as well. Now, from our perspective, data encoding in DNA is going to be accessible to the marketplace, we think, at a reasonable price, et cetera, within 2 years. And there are a lot of issues that still need to be overcome. but I think that's a reasonable time frame to start looking at early presentation in the marketplace of this kind of capability. The kinds of problems that have to be overcome are not terribly dissimilar conceptually from a lot of the things you see going on in quantum. You're looking at error correction. You're looking at how to manifest consistency through time. A calculation done on Monday can't take dramatically longer than a calculation done on Wednesday for the same amount of data. And of course, you have costs and other considerations here as well. But these issues are solvable, we think. We think that it creates an opportunity for a very low energy kind of environment as well, since most of the chemical reactions take place here at ambient or near ambient temperatures. So we don't have to do anything terribly exotic to make this go. And there are a lot of different kinds of models that one could contemplate here, as well as you can see. So once you begin with this graphical and this combinatorial kind of representation, you can begin to play with this in a lot of different ways. You can create compound models, et cetera, et cetera. So from a computational space, we think of two categories, two gross categories, contemplating a taxonomy approach. One is search, because one can create probes and things to go and find targeted molecules pretty easily with DNA. I will also tell you, by the way, that it's data volume invariant. So if I'm searching for a particular molecule out of 1 billion and you say, how about 1 trillion or something beyond that, more or less the same time, all right? So another interesting feature of DNA. But you have to suspend certain conventional ideas. Things aren't organized by media. They're not organized by location. I've just got a liquid mass with a bunch of molecules floating around in it. So how do I know where this data is? And in our encoding scheme, each one of our molecules explicitly encodes an address in a bit stream, and implicitly whether that's a 1 or a 0, right? So search is one category. We've got about 3 projects going on in that area right now. And then the other category is computation, defined as the application of an operator against information that already exists to create new information. So a trivial example would be you have a file of the numbers 1, 2, 3, and 4. Search would be something like, I could find 1, 2, 3, or 4, but I'm not creating new information. Computation in our lexicon would be, I put an operator against this, like a plus sign. And now by applying that to 1, 2, 3, 4, I have a new piece of data or information called 10. Our approach to compute is reasonably varied. There are branching schemes that we can apply against this tree graph, which we think are going to be rather productive to pursue some categories of very interesting problems. Some of the problems that we're looking at right now include satisfiability, which as a class incorporates discrete optimization. We think that it might be able to deal with certain intractable problems there much more easily than what you might find in an electronic construct. We're looking at applications in machine learning. We're looking at applications in digital signal processing and related kinds of fields. We will never assert that this is going to be a replacement for general or conventional computing by any means. We think, like quantum, it'll carve out a set of domains of applicability that that will hold some merit to certain segments of the user space that we're trying to attend to. The other thing I would say is that there are already hints of where some of this is going. So, for example, there's a company in Europe, in Norway, called Pickle, P-I-Q-L, which advertises a long-lived tape technology, and who is engaged in a project right now to try to preserve all music. MP3 music files, like 3 megabytes, something like that they're going to put this on this tape and they're going to put it up in the Arctic repository where they keep seeds and so on north of the Arctic Circle. It's an example of write once, read never, which is the sort of glib characterization that's beginning to emerge in the computing space of how people want to conceptualize how some data is stored for resolution of profound catastrophes at some point in the future, but not with an anticipation that conventional data access latencies and other kinds of things can be realized. Okay. Pickle advertises the duration of its tape to be 4,000 years, right? And which is nice if it's true. But you know, DNA, can I hear 500 million years, something like that? And you say, well, this is all a joke because nobody's going to be around for 500 million years and so on. And we understand that. But pushing the envelope of the longevity of data storage, we do think is important here to teach us more about what's going on. Collection of some papers on using molecules for computation, in some cases DNA. There are recent papers from Microsoft on this as well, which are not included here. Adelman's paper on the left, Traveling Salesman Problem, is probably the first paper that most people read about in this space. I think it's 1996, if my memory is correct. And people have gotten more exotic about this over the course of time. I'll note, however, that all this experimental work, all these papers and so on, are really fundamentally predicated on benchtop chemistry. And one of the other reasons we built the machine we did was to see if we could really do computation at scale with a device like that. All right. So if I can do 500,000 chemical reactions a second using DNA, can I manipulate that in some way to create data representations and instructions encoded in DNA that would be useful? So the reason why that's important, by the way, is that our observations of operating at this scale have begun to change our perspective on what some of the conventional rules of thumb are that people apply to DNA chemistry in general, and certainly with respect to DNA used in storage and other kinds of venues. You don't observe that until you do things at scale. And some of this stuff is actually quite shocking. So it's been a good pathway of discovery. And no, we're not going to talk about that here. We'll let other people figure that out on their own. But it's really, really important when you're doing work in this area to do things at scale to see where it takes you. So summarization of what's going on here is, on the left-hand side, you see DNA conceptualized as a storage medium. So there's density, there's redundancy, persistence. We talked about that. But on the right-hand side is the incorporation of computing concepts with storage. So, you know, to do computing with DNA, you have to solve the storing or encoding of data into DNA first. So we assume the left-hand side, and we're working fundamentally on the right. And it gives rise to the possibility of a single environment where both storage, data manipulation, and compute is done without any real movement between memory tiers. Again, it's fundamentally scale-free, and it's simply relying on native structures of DNA to kind of achieve the kinds of goals that we're looking at here. So, summary, combinatoric assembly of prefabricated DNA, generating symbols. We use that as an alphabet to build more complex words, echoing the kind of Gutenberg-like approach. We put these into a tree structure to facilitate computing. We know that there are benefits in terms of that encoding scheme with respect to scaling at exponential levels. And we can do this pretty quickly, okay? Challenges in front of this, there are many. It's a very target-rich environment. One of the principal issues that I'm working on is how to achieve consistency among chemical reactions, which tend to be stochastic in nature. And if taken too far, of course, they would frustrate people extraordinarily in terms of trying to apply that to compute. So we're working on development of new chemistries, new approaches, new engineering, and maybe some new theories in terms of how to make this as consistent as possible at scale. So that's one domain of inquiry. We're looking for more applications that we can work on with respect to the computing approaches that we're looking at. Right now, we're building instructions and to do certain things. You shouldn't think of this as sort of the conventional, I'm going to write a program and compile it. It's going to be more of an application of a set of operators in a liquid environment to do something against the amount of data that you have encoded in that environment, and possibly at very, very low energy levels. So there are issues like that. We have engineering issues. We have all kinds of interesting issues going on at the level of DNA as well. So I figured I would stop there. You can feel free to contact me at that email address. We're up in Charlestown and Boston. If anybody wants to visit us, you're welcome to. We have a website. You can see what we're doing on the website. And if you want to work with us, give me a call for that too, because we're always looking for people to work with. So that's it. Thank you.
Great, Dave. Thanks. That's a great presentation. I've heard this a few times, and each time it gets a little more clear, and I understand a little bit more. So thanks very much. We have a couple of questions from Steve Poole. Steve, I know you have a couple of items you want Dave to discuss a little bit. So go right ahead now.
Yeah, I don't know if you have time now or not, Dave, but I would be interested in knowing, have you done any comparative analysis between your product or soon-to-be product and MIST, which came out of IARPA,
Yeah.
which was one of the things that I think you referenced because Microsoft was on that program. And then the second question was, and if you can't answer it now, I understand. What do you do about potential externally forced errors? Because they do potentially crop up. How are you going to try to do any risk mitigation on something that would look like in a normal computing environment, a single event or a multiple event upset?
Yeah. So with respect to the first question, you were familiar with the IARPA program. And by the way, there are three other things the audience should take note of. One is there's a current call for proposals from NSF for DNA storage. And there is a Pathfinder, EU Pathfinder project, which requires a response by October of this year coming out of Europe for DNA storage as well. So you can see there's a progressive interest on the part of governments. And there's also been the formation of a Chinese company with the muscle of the Chinese government behind it to operate in this space as well. Although I must say that declarations of what they're doing is a little opaque at this point. What I would say is that we think that everything will kind of move in the direction of some sort of a hybrid electronic chemical kind of representation here. So in our case, for example, and I think in the case of what you see at MIST and some of these other things, you see the incorporation of microfluidics, laboratory on a chip, ideas like that are percolating along. Because one of the things you want to do, of course, is radically reduce the amount of chemistry that's taking place, not in terms of the number of chemical steps, but the actual amount of chemicals, right? So if somebody says, well, I want to encode an exabyte, you can't say, by the way, do you have a rail spur to take all the cars holding all the chemicals? You're going to need to do this. So we need to get this stuff down to probably femtoliter level kind of chemistry. And by the way, we have projects going on in this area as well. That's point one. Point two, we still think that we're quite far ahead of everybody schematically and practically in terms of understanding the issues that swirl around scaling. It's very hard to get away from base by base molecular biology without going down a path of radical parallelism, And that brings with it a whole bunch of issues as well with respect to errors and how you deal with those. So there's more to be said on that. With respect to externally forced errors, we're actually in the preparation stage of writing a paper on errors here, because guess what? Mutation can take place and little odd things like that. I mean, not well,
Exactly.
I guess technically you would say it's mutation, but interesting malfunctions. Let me put it that way. In terms of the combination of pieces of DNA, is a really deep area of study for us now. We've done an extraordinary amount of modeling and simulation on this, trying to bring in both conventional theory, but also our empirical data, which as I've alluded to before, is beginning to raise some questions about conventional theory, shall we say. There are, as I said at the outset, 144 different oligonucleotides in our library. And you begin to see interesting phenomenon depending on how different or how similar they are to each other, right? So it's an area of deep study right now that's got to be resolved. We actually have a lot of thoughts on that and how to remedy that. Eventually, what it comes down to from a read perspective is, of course, you're looking at signal and noise ratios. And right now, if you look at the conventional tooling in molecular biology, if you have a sample of DNA and you amplify it, well, you're going to amplify signal and noise in a ratio proportionate to each other. So we've actually worked out strategies of how to separate signal from noise to do separate amplifications to make reading the output that much easier. So it's a robust area of inquiry, and absolutely we're looking for collaborators, guinea pigs, experimenters, and if you want to work for us, we'll do that as well. We're hiring all the time also.
Thanks much.
Mm-hmm.
Great. Well, thank you very much, Dave. Really appreciate that. And I want to thank all the speakers for a really fascinating morning. I hope people listening got as much out of this as I did. So it's that time where we're just going to have a couple of closing remarks from some of the organizers. Brajesh Gupt from TACC, Jeremy First from BP, and if maybe we can get Keith Gray to say a few words, that would be cool as well. And I know you've already heard enough of me. So gentlemen, why don't you just tell us a little bit about what you heard this morning, what you liked, what surprised you, or any other thoughts you want to share in the next 10 minutes or so.
Yeah, I can go ahead first if you like. Hello?
Yes, we hear you.
Yeah, great.
Go ahead.
Yeah, so before you go ahead, I just had a small question from David's talk. So has the possibility of using DNA storage as random access memory been explored at all, or is that a completely ridiculous question I'm asking?
No, everything is random in DNA. So I don't have a constraining physical media. I just have molecules floating, if you will, crudely put. And what I need to do is just design probes or collections of probes to go after what I'm looking for. Mm-hmm. And by amplifying those probes to a great enough volume, I just throw it into the pool and I get what I'm looking for. So everything is random.
Yeah. So how difficult do you think it's going to be? And would it be, could it compute with the readout rate of current runs or like that?
I'm sorry, that broke up a little bit.
Okay. So I'm asking, what are the challenges in designing a RAM with DNA, and do you expect to have a faster readout rate as compared to the current RAM?
Yeah. So a couple of comments. I spent most of the time today talking about writing DNA. Reading DNA is a problem, right? And that's because the market that exists to build devices to read DNA is focused on precision down at a base level. So if you look at Illumina, or Oxford Nanopore, or something like that, they want to tell you what your genes look like, which means they need to know the sequence of ACGT with some accuracy. I don't need to know that, right? I don't need to know that because my DNA has been prefabricated for me. I know the AGCTs in each of my oligonucleotides. What I need is a reading capability that is at a much grosser level. And yes, we're working on that while we speak as well. So there is a dramatic incompatibility measured in orders of magnitude between write speeds and read speeds. It's got to be remedied before you get this to the level of practicality that I think we would all hope for. But there are people working on this, including ourselves. We have some nascent partnerships we're working on as well. It's a really, really rich area of examination that's being contemplated right now. It's divorced, in other words, from the market dynamics of genomic sequencing. Those guys are too slow because they've sacrificed speed for accuracy.
Yeah, sounds good. Great, thank you.
Mhm.
Yeah. So this morning we heard like very great talks from Stef, Clena, and Stephen about quantum technology. And as you know, I mean, as all of them pointed out, quantum computing is fundamentally different from classical computers. It's not like quantum computing is not like a classical computer being on asteroids. It's fundamentally different the way information is processed and the way computing is done. So that is more so the reason to think that quantum computer is not going to replace classical computers, at least not in like the near future, and most likely like ever. I mean, in some sense. But quantum computers can be used as complementary and as a as an accelerator to to help the classical to help solve a problem using both classical and quantum devices. So in that sense, I think that the paradigm of quantum computing is always going to be some sort of hybrid approach. And like I love the analogy that Stef pointed out, the analogy of a plane and a car. Like invention of plane didn't rule out the use of car altogether. So that's that. And definitely, like quantum computing is in a nascent stage at the moment, but different future is promising, as you know, because the progress is being made at all fronts, like academic, business, and application, and all the industry level, both in near term and the long term. There are several promising areas. For example, in near term, I mean. There are quantum inspired algorithms where the ideas of quantum algorithms can be used to expedite the classical algorithms, and in long term, basically we hope to have the fault tolerant quantum computers which can run the hard quantum algorithms which can give exponential speed ups. And currently, the model of accessing a quantum computer is basically based on cloud access, which is the most popular at the moment, and most likely that is going to be dominate the operations in the foreseeable future at least. And like as Stephen pointed out in his talk that Los Alamos hosted D-Waves machine, which I didn't know that it was already decommissioned. But places like national labs or big companies, they will most likely host these quantum computers, which can be accessed via clouds. And so along that line, I wanted to ask a question to Stephen, like what are the future plans of Los Alamos, of buying or having a quantum machine of their own. So, I mean, maybe Stephen can comment on that later.
Sure.
Yeah. At TACC, currently, we are, I mean, at the moment, we are not interested. Yeah, at TACC, we are at the moment not interested in buying a classic quantum computer and having it in-house, but maybe that can change in a few years. Currently, we are exploring, the strengths of developing quantum algorithms, hybrid algorithms, and so on and so forth. most recently in collaboration with scientists at Applied Research Laboratory here at UT Austin. Among other things, I have been working to push the simulations of quantum circuit using state vector and tensor network simulations. And in addition to, simulating these quantum supremacy kind of circuits, we are trying to build realistic noise models, which will be important not only to, test the algorithms on the NISC devices, but also to characterize and test error correction codes, which are being developed over time, towards the fulfillment of a fault-tolerant quantum computer. And yeah, and apart from this, I would like to mention another project that I have been, working that has to do with quantum computing, but not like totally quantum computing, and that is in the direction of quantum communication. So this project was funded by NSF, and it has to do with designing a quantum joint detection receiver to, decode, the to basically receive signals in a deep space communication where the photon number is quite low, and to decode those signals using quantum hardware, such as the ones being offered by Xanadu domain rather than the qubit domain avenue, where classical hardware, in the sense that it has been proven that using these kind of quantum joint detectors, one can achieve the so-called quantum Hellstrom limit of minimum error probability. So basically, using quantum joint detectors, one can have a very small error probability in detecting these photons. And the interesting thing is that it's been proven that classically, no classical hardware can achieve this error probability. So what we are trying to do is first, basically using simulations and using the photonic quantum logic, we are trying to design these fundamental gates and build a quantum circuit and see, or by a simulation, how, what best we can do. And then we would like to, port this to the NISC devices, basically the one currently being offered by Xanadu, because this is all photonic based on continuous variable scheme. So, and so that's what we are trying to do, and find out what, how else quantum hardware can, help, beat the limits of the classical computing and or classical communication. So this will be useful to detect optical signals in low photon regime, which could be useful in deep space communications when we are trying to get signals from like very, far planets, or these deep space missions which are sent to beyond our solar systems and so on. So yeah, so I just wanted to give a quick overview of these things, and yeah, that's all from me. Thank you.
Great, thank you, Brajesh. Appreciate the comments. Jeremy, I know you wanted to say a few words here as well.
Brajesh, you bring up a good point, and it's something that we didn't actually have time to talk about much during the rest of the workshop, but it's the interplay between classical HPC and these emerging technologies, whether or not we can simulate them and verify the results that before we start spending money on accessing an actual quantum device, porting the circuits onto a classical architecture and simulating them. And I think that's, I don't know if I have much as a question as much as just to say, I think that's going to be a major focus for people exploring quantum technologies, is to bring it in-house and simulate and verify before spending the money to partner with third-party companies and access real quantum architectures with the noise that comes along with them. So I just thank you for bringing up that point there.
Great. Well, thanks. I see we're just about on time here. So I want to thank the organizers, all of the speakers for their great insights, and the participants who came, and some of them who left already. Appreciate it. And I hope everyone had a had a useful meeting, and maybe we can get it together again and do this next year after the energy conference. But I want to thank everyone for listening and hope everyone has a good day from here on out. So long.